Hello everyone, it's MK the guy. Today we are going to look at penicillins. Okay, beta-lactam antibiotics, but specifically penicillins. What do we need to know about penicillins concerning clinical pharmacy and application in medical field? We are going to talk about the structure of penicillins. The beta-lactam ring, they say it's strange. That's why most of the reactions they occur at that beta-lactam ring. How is it strange? We talk about the mechanism of action, protein, penicillin binding proteins. We are going to talk about the chemical degradation. How is it degraded? This one about acid and bases. Then bacterial resistance, extended spectrum, protein binding, allergy to penicillins, penicillin salts and suspensions, then beta-lactamase inhibitors. So let's begin now. Concerning the structure of penicillin, this is the general structure of penicillin. It is, we're counting from this one: 1, 2, 3, 4, 5, 6. So this structure from here is 6 amino penicillinic acid. So that 6 amino penicillinic acid has a beta-lactam ring and a thiazoridine ring. These two rings together they make up a phenam ring. So all the penicillins, they have this structure. What changes? It's only the R group. It's the one which differentiates all other penicillins. Okay, each one from others. Now they say that the beta-lactam ring is strange. How is it strange? Because we see most of the all the reactions. Let me say most of the reactions. This ring breaks here. Breaks here. Why is it breaking there? Not here, not here, not here, not here. Hope you're getting me. This ring is strange in such a way that these angles, they are not supposed to be like that. These angles. Remember, in chemistry, if an atom is bonded to 3 other atoms, they are bond electrons. These electrons, those bond electrons, they repel themselves maximally, such that they reduce the repulsion. They will repel themselves in such a way that they reduce the repulsion between themselves. So if a compound has if an atom has 3 other atoms bonded to it, it will have these angles between these atoms to be at 120 degrees. If an atom is bonded to 4 other atoms, these atoms, they will propel themselves maximally. It's the same reason. So we are expecting these angles between these atoms. This one's like it's facing the other side of the board. This one is facing us, this side. This one is on the board and this one. So this atom, this molecule, the atoms bond pair electrons on the atoms repel themselves maximally, such that they reduce the repulsion. So we're expecting this angle to be 109.7 degrees. Then if an atom is bonded to 3 other atoms, but that atom has lone pairs of electrons. So as if this one is a bond, but these electrons, they are free. They are not bond electrons like these ones. So we expect the lone pairs of electrons repel these bond pairs of electrons more than these bond pairs of electrons repel themselves. Meaning that at the end, this angle, though it looks like this one, the structure looks like this one, but this one, the angles will be reduced because of the lone pairs of electrons. So this angle will be 107.5 degrees. Now, when it comes to this structure, we are seeing this carbon. This carbon atom has 3 other bonded atoms. It has oxygen, nitrogen here, and a carbon there. So this angle was supposed to be 120 degrees, but it was forced to become 90 degrees in this structure. It was supposed to become 90 degrees. It was supposed to be 120 degrees because of the general structure. Then this angle, we are seeing this carbon bonded to 1, 2, 3 bonds. And remember, there is a hydrogen on that carbon. So we expect these angles. Okay, this structure looks similar to this one. So we expect these angles, all of them, to be 109.7, but they are also 90. Are you seeing the strain? This angle is supposed to be 109.7 degrees. This angle, it is a carbon 1, 2, 3, 4. There is hydrogen also. 4 atoms are bonded to that carbon, meaning this carbon, all the angles are supposed to be 109.7 also. Should be 109.7. When it comes to this nitrogen, it is bonded to 1, 2, 3. But this nitrogen has lone pairs of electrons, meaning it should have this orientation in space. The geometric orientation of this nitrogen with the bonded atoms should be with these angles. So we expect this angle to be at 107.5 degrees. So meaning that this angle is too big. This angle is small. Even this one is small. These ones are small, but this one is smaller than these ones. So when you are comparing, this one will be bigger. This one is intermediate to these two. This one will be the smallest. Meaning they got the biggest angle with the smallest angle. It's not 90, but with the smallest angle. So they forced them to bond, form this square angle, the 90-degree angle, meaning that the force was very much, meaning that at any time, that's why all the reactions at any time when the penicillin is weakened or inactivated, this angle will break here, not here, not here, not here, and not these ones. So we have talked about the structure 1. We have talked about the ring strain 2. Now let's go to the mechanism of action. The mechanism of action of penicillins, it is the inhibition of the enzyme which is responsible for the synthesis of the cell wall or peptidoglycan synthesis. So that enzyme, if it's inhibited, there is no strengthening of the cell wall, meaning that the cell wall will be weakened. That enzyme is called transpeptidase. So If this enzyme is inhibited, meaning that there will not be formation of the peptidoglycan or dipeptidoglycan. Listen. Synthesis. So, inhibition of the dipeptidoglycan synthesis. How does it occur? Take this one as the normal mechanism of cell wall synthesis or of dipeptidoglycan synthesis. This one is our enzyme transcriptase. These are the receptors or the active sites of this enzyme. At the active site, there is a nucleophile represented by OH of the transcriptase. So this OH, we know that enzyme is responsible for the synthesis of the peptidoglycan. It will cleave the D-alanine. The D-alanine, if it is cleaved, the remaining D-alanine will combine with the glycine to form a bond such that we get the two chains together, the dipeptidoglycan. This di meaning two. So this OH, it will bind to the D-alanine. Then the peripheral D-alanine will be cleaved off, meaning that we shall have the peptidoglycan peptide chain with one D-alanine. With one D-alanine. This D-alanine is now bonded to the OH group. So, as this glycine forms a bond with this D-alanine, this one will break off. When it breaks off, it will take the proton. So we shall have our peptide chain with the D-alanine bonded to glycine, and this glycine is on another peptide chain. So this bond is not permanent, so it keeps on cleaving those D-alanine, forming the dipeptidoglycan. So these dipeptidoglycans are the one which strengthen the cell wall. Now, what do penicillins do? When it comes to penicillins, they mimic the structure of amino acids. When you come to this structure here, take this part and the upper part. We see that this part has a carbon, has a carboxyl group. Here there is hydrogen, and this part is bonded to nitrogen. Then the other side is like that. So because of the bond, this one was a carboxylic acid and this was the amino group. They bonded for the amide. So we get this one. This is an amino acid. The basic structure of amino acid has the carboxyl group, has the amino group, then there is a hydrogen and the R group. So this is the R group. When you look at this one, it is the valine. It is the valine amino acid. When it comes to the upper part, there is this carbon. That carbon, put it here, it has carboxyl group. Okay. Of course, as I said, this one has a carboxyl reacting with this one. Carboxyl and amine get the amide. Then there's a hydrogen there. There is amine. It's amines there. Then there is this group. Then S. So this structure mimics the cysteine. This is cysteine. So this penicillin is from alanine and cysteine, L-valine and L-cysteine. That's how we get the penicillin. Now remember, we killed the D-alanine. D-alanine. Now we have penicillin instead of D-alanine. So this penicillin will, the OH group will then attack this carbon. When it attacks that carbon containing the O, this bond will be cleaved. As we said, the ring is strained. So all the reactions, most of the reaction will end up breaking the beta-lactam ring. So as this bond breaks, we use these lone pairs to attack the proton, meaning that we shall have now R. We shall have that the penicillin is bonded to the binding site, but the ring has been broken. So this ring has broken, so we shall have this. Now this glycine, this peptide which had glycine, it will not be able now to bind. The peptide chain which has glycine, now where will it bind? Nowhere. So it is inhibited. Also, we shall have this. Even the water which would have brought about hydrolysis will also be inhibited by the structure of the penicillin. So this water, remember, it could have hydrolysis of this bond, but it will also be blocked. It will be blocked, meaning that we shall have penicillin binding permanently to the enzyme. So there is no formation of the peptidoglycans. Now, the mechanism of action is also done. Let's talk about the penicillin binding proteins. When it comes to penicillin binding proteins, they are the same as the transpeptidase enzymes. That's where the penicillins bind. So transpeptidases are the penicillin binding proteins. We have as many as 7 penicillin binding proteins. We have penicillin binding protein 1A and 1B. We have penicillin binding protein 2. We have binding protein 3, binding protein 4 up to 6. Those are the 7 penicillin binding proteins. Penicillin binding protein A and B, they are responsible for the elongation of the peptidoglycan chain. They are responsible for the elongation of the chain, peptidoglycan chain. So if they are inhibited, meaning we shall have spharoplast. If they are inhibited, we shall have spharoplast. Meaning this bacteria will be lacking some part of the cell wall. So we shall this shall result into the cell death. Then penicillin binding protein 2 is responsible for the maintaining of the bacilli, those bacteria with odd-shaped body. So they will have, this one is responsible for the maintaining of this shape, the bacilli shape. So if this one is inhibited, we shall have rounding and oval shape of the bacteria. So it will also result into death. Then penicillin binding protein 3 is responsible for the formation of they are involved in the cell division. For the formation of the septum, which is the cleaving point to make other bacteria. Remember, division by binary fission, meaning that it will divide into 2. So there will be formation of the septum. So this one is responsible for the formation of the septum during cell division, meaning that if it is inhibited, we shall have the formation of the bacteria, which is very large because it won't be able to divide. Meaning that the consumption will be high, the nutrients. So this bacteria, it won't grow like other bacteria, of course. Much consumption. Then 4 to 6, these are responsible for the cleavage of the D-alanine. Cleavage of D-alanine. They'll be responsible for the cleavage of the D-alanine. So let's talk about chemical degradation. These penicillins are unstable in acidic pH and they are unstable in very high basic pH. So they are stable at neutral pH. So we shall have the acid instability and the base instability. Let's do the mechanisms and see how do they occur, such that we can really explain the bacterial resistance and these other parts. Also the chemical degradation itself. Now, this is our penicillin. In acidic pH, meaning we shall have a lot of protons. Remember, this nitrogen has lone pairs of electrons, so it will attack this proton. When it attacks the proton, meaning that this nitrogen will have excess bonds and it has used its lone pairs of electrons, meaning that it will try to stabilize itself to break that bond. When it takes the bond electrons, this carbon remains unstable because it shall have now only 3 bonds instead of 4, meaning that it will become partially positive. So this oxygen has lone pairs of electrons. This oxygen will attack or will stabilize this carbon. When it stabilizes this carbon, meaning that it itself it will be unstable. It has used its lone pairs of electrons. So we shall have the breaking of this bond. When it breaks this bond to stabilize itself, this carbon will be unstable also. So this nitrogen has lone pairs of electrons. So it will try to stabilize this carbon by forming a bond there. Meaning that we shall have now penicillin, which is this all is now having one bond. This nitrogen has formed a bond here, but it has hydrogen, so it is plus. Now this one has formed a bond with this carbon, so it will be like this. Then there is our O. Now this nitrogen took the proton. Shall have S. Shall have this as our penicillin. We shall have this. This nitrogen is also unstable, so it will try to stabilize itself. When it stabilizes itself, meaning that this carbon again is unstable, we shall have this one forming back the bonds. When it forms back the bonds, meaning that it will be also unstable. It will break this bond again back. When it breaks this bond, to take the bond electrons, this one is unstable. So we shall have water. This water will now stabilize this carbon. So our R group, now this nitrogen is stable. This one is back. It's back with 2 bonds. Now here we shall have the O with the water present. So we shall have this, but this oxygen is now plus. We shall have this. This hydrogen, it will be lost. This hydrogen will be lost to stabilize the oxygen. So when it is lost, we shall have R OH. We shall have OH group. This nitrogen with H. We we shall have that, meaning that this is stable. They are all what? They are all stable. Now we shall do decarboxylation. This oxygen will form a bond. When it forms a bond, meaning that this carbon will have excess bonds, so it will break this carboxyl group will break off, meaning that the bond electrons are given to these two carbons. So meaning this one is stable, but this one is having excess bonds, so it will break this bond. When it breaks this bond, this sulfur group has a lot of electrons. Now it will take also the proton. To take the protons. So we shall have our R. Now we have formed a double bond here, and this one we have lost a carbon dioxide. The carboxyl is lost in form of carbon dioxide. Then this bond is broken. So we shall have NH with S with hydrogen. That will be our product there. So it's a double bond. That will be our product there. Meaning that when it comes to a double bond, this double bond is very, very reactive. It's very reactive, so it will also take the proton in the solution. So when it takes the proton, this hydrogen, if it goes here, this one will be unstable. So this one will stabilize that. When it stabilizes this one, meaning that we shall have R. The ring is back. And this bond is lost. It's lost. Took the hydrogen, the other one closed. So we shall have this hydrogen will be taken also. Will be taken by the water. So as this one takes the hydrogen, so hydrogen gives the bond electrons to sulfur, so it will be taken. We shall have this at the end. It's not yet done. The instability of penicillins, at the end we shall have the penicillamine and the penicillaldehyde. So we shall break this penicillin into two. A lot of proton in the solution. Sulfur will attack the hydrogen. This one, the nitrogen, has a lone pair of electrons who form a bond there. We shall have R. Okay, we shall have R with nitrogen. It's R. They are all nitrogen. We have formed a double bond. So meaning that this nitrogen is now unstable. So it has a plus. The ring will break, because if this one forms a bond, this one have excess. So this one breaks, we get the hydrogen, meaning that this bond broke off long time ago. So we have this. This is hydrogen. So nitrogen is unstable. It will take the bond back. As it takes the bond back, meaning that this carbon is left stable. So water will come and stabilize this carbon. So we shall have R, nitrogen is there. Now this bond we having the water. Of course, as here one hydrogen will be lost, we shall have OH with nitrogen and H. Okay, let me make this bond to be like here. So our SH will be there and CO2H. This oxygen has one pairs of electrons, so to form a bond. When it forms a bond, this one will have excess, so this one will go. So we shall have R with NH. Then this one, there is O. This hydrogen will be taken by water again, so we shall have O. Then this silent hydrogen here, which is not shown, it's the one which is here now. Here. This is the penicillaldehyde. Then plus this one has broken off. When it breaks off, this nitrogen will have excess electrons. So having excess electrons, it will take the proton. So nitrogen will have 2 protons with the CO2H and SH. So that is the penicillamine. So penicillaldehyde and the penicillamine will be the end products. So if there is excess protons or acidic pH, that will be the mechanism. Proton, this one, we shall form a new ring. Forming a new ring, this one will be breaking. At the end, we shall have this. Penicillaldehyde and the penicillamine. That's the acid instability. Now, when it comes to basic instability, let's see how it comes. So for base instability, meaning that we shall have a lot of base. So here we shall represent the base with hydroxyl group. So this hydroxyl group it's a nucleophile, meaning that to attack this carbon, when it attacks that carbon, of course, we shall have the carbon having excess bonds. So this one will break. As it breaks, we shall use these bond pairs of electrons to attack the hydrogen. But that hydrogen will be from our water. So we shall have R now here we shall have the OH bonded to this carbon here. The ring has broken, so we shall have N with hydrogen. So here we are. Like the previous mechanism, of the acid instability. This is penicillinic acid. When we reach penicillinic acid, we shall have decarboxylation. So our decarboxylation, like the other mechanism for the acid instability, as this one breaks, these bonds are given to this. This one will break. So this one, instead of now the hydrogen in form of proton, we shall have water. So to take the hydrogen from water. When it takes that hydrogen, we shall form more OH group. So now we form a double bond here with S. Mean this bond has broken off. So with N, H, S, H. So this is what we have. So the remaining mechanism remains the same as for the acid instability. At the end, we shall form the penicillinic, the penicilloaldehyde and the penicillamine. So it's the same mechanism. But what changes, where we use the hydrogen, we are using water. Where we use the water attacking, we shall use the OH group. The mechanism remains the same.